I had a couple of things here, but if anybody's got anything specific, why don't I go ahead and get things moving, and then I'll address any issues anybody might have. I found some statistics that I thought were interesting regarding inverter usage. And I don't know if these statistics are residential or if they're total. I suspect they're residential. But it was a comparison between Enphase and SolarEdge, which are the two main inverter manufacturers, certainly in the residential market. And if you looked in January of 2019, Enphase had about 24% of the market share, and SolarEdge had about 56%, which basically leaves about 20% for everybody else. And then January 2020, Enphase had gotten to 36%, with SolarEdge about 52%. So now they're up to about 88%. Okay, it jumped out on me there. So I think the last thing I said was January 2020, 88% between the two of them, 36% for Enphase, 52% for SolarEdge. And now it's 48% Enphase, 40% SolarEdge. So Enphase microinverters are actually surpassing in the US SolarEdge, which I thought was interesting. Okay, any reactions to that?
I agree.
Yep.
I agree. At some point, Enphase had some serious problems, and where their stock price went very, very low. But I'm glad they're coming back. I have Enphase, M190s, I think.
Yeah.
And I had somebody call me the other day regarding the IQ7 upgrade.
Yeah,
and
I think,
also might mention, you know, you go ahead.
Oh, I was going to say, I think a lot of the growth is because they've added a battery option. You know, people were a little hesitant going with microinverters because there was no battery backup option. Another thing I thought I would bring up is one of the things that's out there in the media quite a lot is the fact that panels are going to larger sized wafers. And so I did a little bit of research on that. It seems that about 40 years ago, the cells themselves were about 100 millimeters square, which I guess runs about 4 inches square. And then by the 2000s, they had increased to about 125 millimeters, which is about 5 inches. And then in the last 7 years, they started calling them like M1, which the M1 cell was 156.75 millimeters. And then there were some subtle variations in recent years, all the way to the M4, which is 161.7 millimeters. And then all of a sudden, just in the last year, things have gone crazy with this. They introduced the M6, which jumped up to 166 millimeters. Then the M10, which is 182 millimeters, and now the M12, which is 210 millimeters for these cells. They're anticipating the M6, the 166 millimeter, will probably be about 70% of the market by the end of this year. But to give you an indication of the different sizes, I mean, the M6 can generate about 13 amps. And we're talking, you know, before we were looking at about 9 amps was about the average on a panel. But Trina Solar just introduced what they're calling their G12 panel. And it's a 500-watt panel. And it uses the M12s. And it's 7 feet by 3.5 feet in size, weighs 65 pounds, and is a 50-cell solar panel. So we've been used to 60-cell and 72-cell. This is a 50 cell, but it's still 7 feet by 3.5 feet, which is huge for a solar panel. And the 65 pounds, one of the things that they had been trying to do for a long time is keep it below the 50-pound OSHA threshold. Because OSHA says if it weighs more than 50 pounds, it takes 2 people to move it, to lift it and stuff. But this 65 pound, apparently they're just not caring about that anymore. My guess is people weren't abiding by it anyway. It's not like OSHA's standing out there looking over everybody's shoulder. But also I know from my own experience, even a 50-pound panel is too awkward for one person to handle easily. You know, you're going to want 2 people working with it anyway. So I guess it doesn't really matter if you've already got 2 people that you're up over the 50-pound threshold. So I think we're going to continue to see that, is these panels are just going to get bigger and bigger and bigger. There's got to be an upper limit, but you know, the sense is that if you've got larger panels, the amount of time that's involved in installing it gets less. If the efficiency increases, then the balance of systems is less. So, you know, a 7-foot panel is a pretty hefty panel. So
I have a short movie of a few minutes, about a minute, of a guy carrying a single panel in a Chicago windstorm. If you want.
Oh, do you really? You want to share that?
Yeah.
Okay, let's see. This is probably, is it Buster Keaton?
No, it isn't. So my desktop. See those guys there?
Yeah, those people look like a motley crew.
They are, but I love them to pieces.
Yeah, that's a pretty hefty, large solar panel there, unless the guy's short.
I'm for sure that wind was going to take.
This is when I learned that you need a 22-foot truck, not a 16.
Oh. Well, at least you're doing a 1-story roof there where you can just hand them up.
Yes. I went out and I bought a Honda-powered levitator that's in my garage still.
Yeah, I forget which class it was. We had one of the classes where someone was talking about, you know, laying plywood, and they were up on a roof and the wind took it while the guy was holding it, and he just parasailed down to the ground off of the roof, which seemed rather fortunate. But so I still, you see that guy moving it like that, and that to me is just an injury waiting to happen, you know, because he's in an awkward position. You've got this solar panel. I think moving those panels around really is a 2-person job to do it safely, because that's just an easy way to hurt your back. Having that thing, you know, you're at a weird angle, and if he slipped or fell or tripped or the wind caught it, it's just not worth it, you know.
I could never tell those guys to do 2 guys.
Yeah, well, there was obviously one guy just standing around filming it, you know, doing nothing. So
See, somebody has to do that.
Could have got him involved. So,
I did. It says, go over there.
okie doke. So, all right. So we talked about solar cells getting bigger. Talked a little bit about the market share between Enphase and SolarEdge. Did anybody have any specific issues or items they wanted to bring up this week? Yep, Bill? You're on mute, Bill.
Yeah,
There you-
okay. I'll share my screen. I went out to visit this solar array in Navasota late last week, and I've kind of prepared this document. It turns out it's 45 kW, and 14 of which is off-grid. And
Okay.
and you remember we showed this, I showed this picture last week of this right here. Can you see that?
Yeah, I can see you're scrolling up through items.
Yeah, so this silver thing on the left is a grid interactive inverter charger from Outback, and
Okay.
it's and I have not been able to contact the guy that knows about this system and why it's not working, but that's what this is, and anyway, that's really all I have to say. I mean, this was a huge ground mount array. I think I got a picture here. Well, maybe I don't.
Yeah,
No, I
you
guess I
showed it
don't,
before. It was, you said 45 kW. That is huge.
Right. This is
Is
a guy
this
with
is this the spec sheet for your the one that's just at the bottom? Is that the spec sheet on the inverter charger? No, that looks.
No, I have not actually pulled that up, but that's the part numbers. Yes, it's 8 kW at 48 amps input from
Yeah,
a battery pack.
Yeah, this is 8 kW. All right. Yeah, that's split phase. Okay. Yeah, this is obviously that's not going to that's got to be connected only into a critical load panel, I would assume.
But if it says grid interactive, utility interactive, wouldn't that imply that it can that it does connect to the grid?
Yes. Yes.
Okay.
What it typically does again is it connects into two different service panels. One is the main service panel that's connected to the utility grid, and then one is the critical load panel. So I think, let me, why don't you stop sharing and I'll bring up the whiteboard and just quickly draw that so if
Right.
people are confused on it. Again, the way that's going to be an inverter charger. So a portion of the array is going to come in. There's going to be some sort of DC disconnect. Then it's going to come into your charge controller. It looks like there were two charge controllers there as part of that. Then you're going to come into your inverter charger.
Well, the
reason-
battery.
Yeah, no, it comes in here first. Then it, oh, sorry, yeah, you're right. Goes into the battery. Then it goes into the inverter charger. All right, and then from the inverter charger, it's going to go into a critical load panel. And then it's also going to go in to a service panel. And then this is your main, and then that's going to go out to the grid. All right, and that's going to go to your telephone poles and your transformer and all that. Okay, so the way it works is as things are flowing through, it's going to check the battery level. If it's charged, fine, it's going to just bypass on through. There'll be a secondary connection. I don't really want to show it, but you know, it's there. So it's going to flow through. It'll go through the battery if it needs to. Then it goes from DC to AC, and it goes out in two directions. So now the energy is flowing from the panel. Charge controller's checking the level of the battery. It'll recharge the battery if necessary, but this is when the grid is operational. And then the power will flow both to the critical load panel and to the main panel. And if it's not generating enough power, it's going to come back from the grid and it'll flow through here and it'll go here. Now, if the grid goes down, what happens is it disconnects there. So now what you've got is your main here. Your grid is now disconnected from the system. That's a transfer switch inside the inverter charger. So now it's going to go from the battery, the array, and it's going to flow through this inverter charger, but it's also just going to go to the critical load panel. So that's the way that would work. And one of the reasons they call it an inverter charger is if we wanted to, we could add a generator here. The generator is going to come in. And if it turns out you've got a day where the solar array is not handling the load, this charge controller is going to, or the inverter is going to sense it. It's going to kick the generator on, and then it's going to charge your battery bank. And that will work. And there's just a port where you connect in a generator here. There's a port where you connect in your battery terminals here. There's some sensor wires that go to your charge controller. It's all labeled. It's all easy to hook up. My guess is the problem is, you know, in the programming of the system, you know, going through all of the myriads of menus and getting everything operational.
Yeah.
But this would be known as a DC coupled system.
DC coupled.
It's grid interactive.
So the processes, the two processes of charging the battery and providing backup power for critical loads, those are parallel. They'll occur simultaneously.
Yes.
Okay.
Yeah.
Well, he does have a 100 kW generator.
Whoa. This guy's, is he a prepper or something? I mean, what? He's...
You know, that's a good question. I got the contact through some preppers, but he drives a Tesla. He's a very retired physician.
Oh, okay. Well, we know how those physicians make all that money. So, right? We're picking on Jay there. But yeah, it's funny. A lot of times in class, I'll make this mention about, well, if you win the lottery, you can do this and that. And I had a class one time where one of the guys who would come in told me that he, in fact, had won the lottery. And he and his family had won $300 million. So that's the kind of person who would put a system like that in. So, Bob, you had a question?
Okay, the circuit that you just showed, I agree with. So I'll give you my stamp of approval that you could put on your book and everything.
Okay, good.
But the last week when you put it up, it was drawn slightly different, and I had some confusion with that.
Yeah, well, last time what we're trying to figure out is it looked like he just had two inverters. And we're trying to figure out how you would make this system work with a generator, but the inverters that he was showing were grid interactive inverters, not grid interactive, but just grid tied inverters. So it looks like this guy's got multiple systems flowing through this.
Yeah, he's got two parallel systems, and they're side by side, but they're not interconnected. Three Sunny Boy 7.7 kW grid tie inverters on one side, and then the off grid on the other side. And that made it.
Okay, what I would do is the manufacturer of those inverters, of those controllers, I would give them a call and talk to their tech department, because they've run into everything out there and how other people connect things. And I would guess that they would have, they can give you drawings and they can give you ideas on what is the best ways to handle these things. And that would be my go-to source. And I've used that many times in my businesses with great success. Subnote, Enphase is not like that. Enphase doesn't have one technical person on their staff, I don't think. But they do have 200,000 videos that the guys you call up will send you on their emails, on attachments.
Yeah,
So-
I think, do you know, Bill, if their Sunny Boys are working? You know, is any part of this system working?
Yes, the 31 kW is working, connected to the grid. I might just add parenthetically that the amount of panels devoted to the Sunny Boys is 31 kW, yet 3 times 7.7 is 22 kW. And however I looked at the specifications of the Sunny Boy, and even though they're only 7.7 kW, you can feed 12 kW into them. So my assumption is that it's generating earlier and later today because it's, does that make sense?
Yeah, what I'm going to show here is what you're talking about there is known as the inverter load ratio. And normally we're talking about a 1.2 inverter load ratio. And what you end up with is what's referred to as clipping. So if you look at a typical sunny day where you've got your array is generating, and just to make it sense, I'll talk about like a microinverter. So let's say this is a 200 and or a 300 watt panel, right? But the same is true for an array. So if you're under standard test conditions, this would be 300 watts. And at solar noon, you would generate 300 watts. And that's all fine and good. So then you would say, well, what size inverter do I need to hook up to this panel? And logically, you would say, I need a 300 watt inverter. But what would happen if you hooked up a 250 watt inverter? Well, then your 250 watts is going to cut off right here. So this part of your production will be lost. So that normally sounds like a bad thing. So then you would say, okay, well, why don't we hook up, I should have the bottom of this like this because it's 0 at night. But if I had a 250 watt panel, then my curve might look something more like this. So this would be the 250 watt panel. This is the 300 watt panel. Well, what you'll find is this loss here is more than what you're losing up here. So with the larger panel, you're still actually generating more power during the day, even though you've clipped off, you know, right at solar noon. And the fact is, for standard test conditions, you might only have a panel generating 300 watts, maybe 5 or 6 days out of the year. For most of the year, that panel is going to be generating less. So they usually figure about a 1.2 ratio is the ideal. And that's largely because the difference in cost between solar panels and inverters, panels are a lot cheaper. So what you would often do is, let's say you'd have a 30 kW array, but all you would need is maybe about, what would this be, about 6, so about 24 kW inverter. And that's going to be a fairly standard way that you're going to design these things. So you were saying with his solar, with his Sunny Boys, these inverters were what size, Bill?
7.7 kW.
7.7.
Times 3.
All right, yeah. So that's going to be 23.1, is that right? 21, yeah, 23.1. And you've got how much of the array is going to it?
31 kW.
31. So what's 31 divided by 23? It's going to be right about a about a 1.25, I'd say, inverter load ratio.
Well, that's more like 1.34.
1.34?
Yeah.
That's a little aggressive, pretty aggressive, but it's still not
Mhm.
out of whack.
Okay.
The alternative would be put another inverter in, which is going to add a lot to the cost, but it might not actually generate much more power. So this is trying to maximize, especially in an area where you're in Ohio, aren't you, Bill?
No, I'm in Houston, Texas.
Oh, okay. So yeah, I was going to say in a cloudy environment, but you might be better. Although you're warmer, so you know you're not going to get extreme cold. But you will often see that the DC input range on these inverters. So what is it telling you is the DC input range on the 7.7 inverter?
Were you
How much-
asking me a question?
Yeah, how much did it tell you you could input DC wise?
Oh, 12,000 watts.
Yeah, so it said you could actually go all the way up to a 12 kW, even though it's only going to output 7.7.
Right.
Yeah. And the reason, you guys understand why we've got the 7.7, which seems like a weird number? Because that's a fairly common number there. And that's because of the 120% rule, right? If I've got a 200 amp panel and I'm coming in here, well, I could maximize coming in with 40 amps. Well, what's 40 amps times 240 volts? What's that going to be? Is that 9,600, right?
Right.
Okay, so a 9.6 kW, except we have to derate this by 1.25 because of the safety margin for the wire and everything. So coming in with 40 amps, we have to give it a 20% or 1.25. So what's 9.6 or 9,600 divided by 1.25?
It's 7.68.
Yeah, 7.68. So you're set as 7.7, but I'll bet you money if you look at it, it's actually 7.68 kW. You know, and that's why it is because that's the maximum size you can load connect to a 200 amp service panel with a 200 amp service from the grid. So you'll oftentimes see 3.8 kW inverters and 7.7 or 7.68. Those are two pretty standard sizes because this one would work with 100 amp service on a 100 amp panel. This one works with 200 amp service on a 200 amp panel.
Right.
So,
Cool.
okay. All right. See,
Yeah.
we learned something sometimes. Anybody else have any questions? No? Okay.
I might say something.
Sure.
You know, solar farms are happening in the Houston area. I assume that's true up in Ohio also. And they need workers, right? I mean, these are 150 megawatt farms, and they've contracted with the local junior college to have a 2-day training, 40% of which is OSHA training. But the goal is to, you know, employ people willing to go work installing the solar farm. And I found that very encouraging going forward, that, you know, jobs, and and it's a good thing.
Yeah, in fact, I was talking to a company out of Texas, in fact, that was doing the project management for a couple of large projects here in Ohio. And they traditionally have done oil field management. Now they're getting into solar array project management. And one of the things he mentioned is Ohio has a law that says, okay, if you're going to do one of these projects, you've got to hire 90% of your workforce has to be residents of the state of Ohio. You know, as opposed to a lot of these pipeline projects where you bring a crew in from out of town and they come and stay in hotels and, you know, then keep moving on. And plus, a lot of these projects are pretty long-term. When you say like 125 megabyte or megawatt systems, I mean, that might be a 3 or 4 year project. So these jobs are going to be around for a while. So, so that's all a good thing. And we're seeing more and more of this happening. And I anticipate with the Biden administration, we're probably going to see some government money being funneled into this. You know, we've already seen the extension of the investment tax credit. So that was scheduled to draw down, but now it's not going to. For these larger projects, they've got the accelerated depreciation, which is a big deal for them. Basically, what they can do is deduct the cost of the system over a 5-year period. So 20% of the cost is deducted each year. So if you're investing, and if you're paying a 30% corporate tax, somewhere in there, you know, that's money right off your bottom line. So those are going to be incentivized. We'll see what other incentives they come along with. You get rid of the tariff, that's going to be a big deal as well, because that's been a 25% monkey on everybody's back, you know, for no purpose other than, I mean, the tariff did what it was designed to do, which was to reduce solar installations. That was its only motivation, regardless of what people said. You know, because the alternative of creating solar jobs was laughable from the outset. I mean, you can't set up a system where you say I'm putting a tax on these things for 3 or 4 years to incentivize people to build solar manufacturing plants that will take more than 3 or 4 years to build. You know, I mean, it just makes zero sense. The only way it makes sense is if the whole goal is just to raise the cost of solar by 25%. You know, that's its only goal.
Interesting.
But we'll see. It'll be interesting. But I really have a feeling once the COVID ends, you know, which it will at some point if people stop going to Super Bowl parties. You know, we'll see. There's going to be a lot of pent-up demand in a lot of areas. You know, I've been thinking a little bit about it. You guys, you know, we've heard a lot more about the Spanish flu and everything. Because of this, I wonder how much of the Roaring '20s was a reaction to, you know, having a couple years of the flu and years of World War I. You know, you've got all of this deprivation, all of this stuff, and then everybody just busts loose. So I suspect we're going to be in for the Roaring '20s again here. People misbehaving.
Well, I got my shot yesterday, and I have to say it was quite a relief to be protected.
What's that noise I keep hearing?
Yeah, it sounds like potato chips or something.
It sounds like heavy breathing.
Maybe somebody's snow shoveling while we're doing this. Yeah, I haven't really worried too much about the getting the shot, except I'm going to be teaching a wind class coming up here in March, and they've informed me that there are already 18 students signed up for it, and it's going to be an in-person class. So I'm thinking that's going to be a little tough, being locked in a room with 18 students 5 hours a day for 7 days. So
Is this wind class to provide workers for installation of the huge turbines?
no, this is a small wind. It's ETA has a small wind certification. So it's really designed for 100 megawatt or smaller systems. Or no, yeah, 100 kilowatt, sorry, not megawatt, 100 kilowatt or smaller wind turbines. So we do, like, give you an example, one of the labs is to raise and lower a 30-foot tower. So, we're not talking about going up on one of those multi-million-dollar units. So, but I only teach.
When I'm out driving around, there's a big wind farm in in West Ohio along US 30 that I think is a Portuguese sponsored place. So those are the commercial sized towers. But what are those per unit output? What's output per unit, and the one you're describing, are those farmers using their own power, or?
Yeah. Even the smaller units, the smaller commercial wind turbines are going to be about a megawatt each. So you're talking serious output. And they usually cost about $1 million or so to put up one of those. But if you divide 1 megawatt by 1 million, you're talking $1,000, per kilowatt, which is cheaper than solar, so about $1 a watt. So, those are a good deal, but again, if you're dealing with that from an instructional standpoint, it's really product specific. So if you've got a GE wind turbine, you've got to have a GE instruction on how that all goes together. If it's a Siemens system, you're going to do Siemens. If it's Honeywell, so it's all very product specific. But we deal with it from a small wind, talking a little bit about aerodynamics, talking about, integrating wind with solar if you wanted to. But there's not a lot of demand for it as far as the certification. Solar has just gotten so much cheaper at the local level that it doesn't make sense. In fact, I like to say, if we're looking at a thing here where, let me just, if I've got one wind turbine here and I want to service one house, we're usually talking about $60,000 or so for that, compared with maybe 15,000 for solar. But what you could do is make it a little bit bigger, go to 80,000, and then you could service 2 homes. Well, now it's getting a little bit, or if we made it a little bit bigger, say $90,000 unit, we could service maybe 4 homes. And then you can get all the way to the, $1 million units, and we could service, 1,000 homes. And so now it's really just 1,000 per home. Well, that's very price competitive. It's cheaper than if we went out and put a 10 kW system on, a $10,000 system on that home. So that's why big wind has been very competitive, but small wind has not. And, when you find that 60, 70, 80% of your project is in the tower, it doesn't really matter. You put a little bit bigger turbine on there and it's going to work for you. So, all right. Did anybody else have anything for the good of the cause here?
Let me show something. I hope you can see this on, how do I make? Well, this is a vertical axis wind turbine tower that fell. Let me see. I guess I can't.
No, your screen share or your background is going to interfere with it.
You got to take off your background.
Okay, so let me see. That would be
Now we're going to see all his dirty
not
laundry in the back. So,
choose virtual background. None.
yeah,
None. Okay.
there you go.
Now, let me see. Let me turn this back on. So this was a junior college that had a vertical axis wind turbine, and about 30, 40, it was a vertical axis wind turbine, and I went out there to inspect it because I was involved with the installation 10 years or 7 years ago. But this,
Yeah.
that's about, I would say, almost 2 feet in diameter, and it snapped.
Snapped at the base. Yeah.
Yeah.
I can, it's funny. There's a vertical axis wind turbine at Zane State right outside the classroom where I teach. And they've mounted it on the patio area right in the corner. And when the wind is blowing, you can see that tower just start to wobble like that. And it's because it's imbalanced in some way. And if you go to the base, you can see that it's starting to just tear the hell out of the concrete right there at the base. So I wouldn't doubt that the same thing's going to happen to that one before too long. It just wasn't. Vertical axis wind turbines are a bad idea anyway. They look cool,
Now,
but they're
Are you saying bad because somehow there's more vibration?
That's part of it, but no, it's mostly inefficiency. If you think about a vertical axis, and there we're talking about blades that are stacked like that, and as they spin, as opposed to, the ones you're used to seeing, which are called horizontal axis. But if you think about blades that are going and they're being pushed by the wind, one of the blades that's being pushed is counteracted by one that's going against the wind. So you're always going to be pushing this thing against the wind. And so you lose efficiency, a significant amount of efficiency. In fact, it's funny, the old Persians developed the very first wind turbines, 4,000 years ago or so, and they did vertical axis wind turbines. But what they did is they built a wall over half of it so that the wind, that as it was being pushed towards it, that wall blocked the wind for half of the wind turbine. And so it was more efficient. It was actually a better design than what we find today, which is interesting. But it would only work clearly if you had prevailing winds that were always coming from the same direction. So just as a little aside on wind, since we're talking about that, I think there's a cute story where back during the Middle Ages, there were really only two forms of industrialized power. One was windmills, that ground grain by blowing. The other was water mills that did the same thing. They ground grain. Well, the lord of the manor owned the river. So he would charge taxes for anyone who built a water wheel or a water mill. But they were having trouble determining who owned the wind. So the Pope announced that God owned the wind, and as God's official representative on earth, he must be paid for all windmills that were constructed anywhere in the world. So they actually had priests and bishops going around collecting from anybody who built a windmill, because you had to pay the Pope for God's wind. So that's...
I was out in Detroit. I was out in Detroit, Michigan, over at Henry Ford's house. And this guy, Thomas Edison, had a stream right next to his house and had one of the first turbines there, generators for his house. Ford had electricity before anybody else did.
Yeah.
In the Detroit area and stuff like that. And they still have it, and it was perfectly preserved. It was just it's a wonderful thing to see.
Yeah, the very first wind turbine, an electricity generating turbine, there's a little bit of controversy, but because two were developed very similar about the same time. But Charles Brush is credited really with developing the first large wind turbine. And he was up in Cleveland, Ohio. And the Brush wind turbine was there actually for like 40, 50 years. It was huge. It had something like, I don't know, 80 blades on it. You know, it would go around. There was a Scotsman who developed a wind turbine in Scotland, and all he did was just powered his own house. And you know, so he didn't get a lot of notoriety. But the Brush wind turbine is really considered the very first commercial wind turbine. So Ohio.
When was that created?
Pardon?
When was that created?
I think it was created, you know, late 1800s, somewhere in there. I'd have to look, you know, it might be 1880s, somewhere around there. There was a lot of electrical stuff going on all at the same time.
Well, in Chicago, if we had an 80 blade generator, we would turn it into a Ferris wheel immediately.
Yeah. Yep. Yeah, I always like to say that Ohio, you know, if you ever see our license plates, it says something like birthplace of aviation or something silly about that, because they like to claim the Wright brothers, who it's questionable whether they were the first ones to fly anyway. But I always think we really should claim birthplace of energy, because we had the very first oil well in North America.
I concur.
Pardon?
I concur.
Yeah, we had Thomas Edison born here. You know, we had the first wind turbine. So we had the first rivers that would regularly catch on fire, you know.
John D. Rockefeller.
The Cuyahoga, yeah, Rockefeller with his oil empire. So really we had a lot more firsts in energy than we ever had in aviation, but they like to, it's not as sexy, I guess.
The problem with being first is your infrastructure is first, and it gets outdated pretty fast, and emerging countries have the better technology.
Yeah, I think, in fact, that's one of the reasons why, you know, we have so much trouble with some of the updating. We've got too much legacy technology. So look at places, 5G and stuff.
If you have, I infer that this tower that's getting its base chewed up at Zane State could really be a safety issue if it's in proximity to students and buildings and things. The photo of the Tacoma, whatever it is, bridge that got oscillating and went down. You know what I'm talking about? It's back when there was a bridge that just had these huge oscillations before it actually crumbled. But I could imagine in a university setting, you'd have bureaucrats who would poo-poo the idea that wind could knock down a tower that's supposed to deal with the wind. But
yeah, I would imagine, although this particular, even if it fell, it's not in a high traffic area, so it might cause some damage, but I don't think it would be to people. You know, it would just maybe swing up and hit the building at some point, but it's just my classroom, so you know, nobody's ever in there anyway.
Okay. And nobody looks out the window anyways.
They put it in the worst spot in the world too, right? You know, maybe 50 feet away from the building, and it's supposed to be located 300 feet away from any obstruction. So it's really just a billboard, which, you know, is going to be a billboard for collapse eventually.
I do have one sub point in here. I have a Nest thermostat.
Yeah.
And the main thing that a thermostat is supposed to do is regulate the temperature of a building from a furnace or air conditioner. Nest runs plus or minus 2 degrees.
Really?
I'm serious. I went online. I'm hitting 68 degrees here, and next thing I know, I'm sweating at 72. And I went online, and there's a whole force there of people trying to get Nest to change it. And Nest is refusing to do anything about it. I mean,
really?
What do you think? What do you think it is? A thermostat? No, it's a spy. It's everything else but a thermostat. Remember Honeywell, where you used to have that little rheostat in there that you used to set? that you
Yeah.
can adjust to your furnace. So that's totally missing, and it's terrible.
I had a guy I used to work with who had been involved with a large contact lens company. And he said, you know, if you've ever worked in an office building, there's always the battle of the thermostats where people, you know, half the secretaries seem to be dying of heat exhaustion and the other are freezing to death, and they're always adjusting the thing. So they put these little cages over them and stuff. Well, he said they went to an automated system. So the thermostats were being controlled, you know, centrally through these sensors and everything. But they went ahead and put thermostats, dummy thermostats, all over the buildings. So people could go and adjust them, but they weren't connected to anything. And then they would put out memos saying, stop messing with the thermostats. So they put little cages over the dummy thermostats, and people would take paper clips, you know, and go and adjust it. But none of them were doing anything, but it kept everybody happy because they were fussing with the dummy thermostats. So, and one other thing on thermostats is interesting. If you remember, a couple of years ago, there was a huge data breach with Dayton, the department stores. I think it was Target. Target is owned by Dayton, and like 1 million people's credit card information, or several million, you were one of them. The hackers got in through the thermostats. Because the thermostats are smart technology. So they hacked in through the thermostat, got to the mainframe, and got to the credit information through the portal that was created by the thermostat. So if you're monitoring your thermostat's usage on your computer, be aware that it's actually a weak link into whatever computer data you have. Somebody could hack in through Nest and get into your computer system. So, welcome to the Internet of Things.
No. We're all plugged in today, and Big Brother has been watching for decades now.
Yeah.
And
I can give a quickie. Go ahead.
Yeah. Okay. Go ahead, Jay, and then Bill.
Oh, quick on the equivalent of the thermostats. Somebody in my dorm would let me drive her 52 Studebaker all the way across campus in the rain to do a middle of the night course. I knew the bypass around the corporate thing, so I could do my puny little machine language programs. And I was so proud of myself for knowing how to use a choke on an old car. Then I found out later that it was a overdrive that didn't work, and I was just playing with a button, and car drove just fine. Would have driven just as well if I'd ignored it.
Uh-huh. Yeah, Bill, you had something? You're on mute again, Bill.
Yeah,
There
I
you
would
go.
just like to propose that next week you talk a little bit about electrical safety. One of the biggest fears I have for an installed system, and generally ground mount, is that somebody gets hurt, shocked badly. And I just like to, you know, have a little bit of a discussion about that, perhaps next week.
Okay. Yeah, just remind me and maybe send an email just before. But yeah, we'll try and talk about some of the safety concerns and some of the things you can deal with, you know, to avoid. You're never 100% safe, but you can minimize the risk.
Sure.
Sure.
Okay.
Okie doke. All right. Well, why don't we call it a day, and we'll get back together next week. Thanks, everybody. Bye-bye.
Thanks, Jay.
Uh-huh.
Thank you. Thank you.